and these are called the comparison tests. There's two of them, but these are pretty common, and they're nice because they're usually definitely a lot easier to use than the integral test. This is called the direct comparison test. We're going to compare this to a series that we already know what happens, and you can kind of see how this test works. It's pretty simple. There's only 2 lines to it right there. So it says, suppose that an and bn are series with positive terms. So we have a series right here. You can call this one the an series. It really doesn't matter. And then we're going to introduce another series, usually a p series, right? So what we're going to do is compare it. And we look at the terms here and say, what are the terms of the series we're given? 1 over n squared plus 3. This is approximately equal to, or it acts like, 1 over n squared for large n. Okay, now when I say for large n, why do we care about large values of n? Because we're talking about infinite series here, right? These series just go on forever. And so the vast majority of this series is large terms for n, right? And so that's what we're interested in. How does the series act for these very large values of n? Well, the way that we determine that is we just look at the highest power. The highest power is the second power. Any power below that, such as the 0 power, is neglected for large values of n. In other words, we just drop it off of there. Okay? So basically drop off any lower power terms. And then look at what you're left with, and then see, okay, well, what happens to this series after you decide that this is the one that it acts like? What happens to this one, 1 over n squared? This converges, right? Because it's a p series. We know now what we're going to do. We're going to compare our series, the 1 over n squared plus 3, to this series that we know what is going to happen. Okay, so here's the comparison then. How do they compare? Well, let's see. 1 over n squared plus 3, how does it compare to 1 over n squared? Well, if you look at it, the plus 3 down here, what effect does that have overall? When you add stuff to the denominator, what does it do to the fraction overall? Well, doesn't it make it smaller? And so putting that plus 3 on the denominator makes the whole thing smaller than the other one, right? So less than. In other words, I know I can put a less than symbol there. All right, and so if you look up at the conditions for direct comparison, look what it says. It says if bn converges and an is less than bn for all n, then an also converges, okay? So basically what we did here is bn was the series right here. In fact, just the terms here, this was the bn here, was the an. And so what did we show? We showed that an, that, is less than bn. So there we go. We've shown that we've got a series here that has terms 1 over n squared plus 3, and we compared it to one we know converges because it's a p series, and we've shown that that less than symbol is pointing the right way, and so by the direct comparison test, we've just shown that this series has to converge. Okay, so our conclusion here is that this series converges by, and then I usually abbreviate all of these. This is direct comparison test, DCT. So that's clearly much easier than it would have been to try to find that antiderivative there and do the whole integral test. So this test is definitely easier than the integral test. So that's kind of just intro to comparison tests. Let's try another one. Let's try B. And we'll find that there is a pretty glaring problem with the direct comparison test. Notice that if that inequality sign is pointing in the wrong direction, then we can't use direct comparison. That's the problem with this. So anyway, the first thing that you're always going to do on these, the question is determine the convergence or divergence, right? That's all you have to do on the problem. When you get questions like this and you've decided you're going to use the comparison test, direct comparison, or even limit comparison, either of them, the first thing you want to do is decide what you're going to compare it to. And so for that step, you just say, okay, for large n, what's going to happen? And so we look at the series that we're checking, and then we just ignore all terms lower than the highest power in the numerator and the denominator. So highest power in the denominator is the second, or sorry, in the numerator is the second power. Everything below that is ignored. Highest power in the denominator is the third power. Everything below that is ignored. And then you can say, okay, well, now that I've dropped off those lower power terms, what does this simplify to? It simplifies to 1 over n. And now we know the series we're going to compare it to. And most of the time, that series is going to be a p series. and this series diverges. Why? P series P equal to 1. So everybody see what I'm saying here? This is your steps. First step, compare, decide what you're going to compare it to. That's, see what happens for large n, okay? Once you've decided what you're going to compare it to, tell me what happens to that series that you're comparing it to and why, okay? Well, what's the series we ended up with? 1 over n. That diverges. Why does it diverge? Because it's a p series, because p is equal to 1, okay? So what I have written here is on the way to being, full credit on a problem like this. So what's the next step now? You make the comparison. What's the comparison? We're going to compare to the series that I know what happens to it, okay? And in this case, I'm actually going to leave it in its unsimplified form because it's easier to check in the unsimplified form. What form is that? That's the form I got right here before I simplified it, okay? Why do I want it that way? Well, because now it's easy to compare the powers in the numerator and the denominator, right? If they're all the same, it's pretty easy to see which one's bigger and which one's smaller. So that's why I think leaving it in the unsimplified form is better here on this step. Okay, now, like I said, it should be fairly simple to tell which one is bigger, right? Because what's happening here? I'm adding a 1, right? If I add 1 in the numerator, that certainly has the effect of making the entire fraction bigger, right? And then also, not only am I adding stuff to the numerator, I'm also subtracting stuff from the denominator. If you think about the way fractions work, if you make the denominator smaller, what effect does that have on the fraction as a whole? Well, it makes it bigger, right? So what we actually have here is two things that are making that fraction bigger than the thing on the right side, right? Adding stuff to the numerator and subtracting stuff from the denominator both have the same effect. They both make the fraction larger, okay? And so that is enough for us to say, well, which way is this inequality pointing? It's got to be going that way, right? It has to be. But this is the series 1 over n. And so if you look at your comparison test there, this is your bn, right? That's your bn. This is your an. Well, what's happening with this series? That's divergent, right? If you look at the second line of the direct comparison test, what does it say? If you have terms of a particular series that are larger than a divergent series, then you must also be a divergent series, okay? So the takeaway from the comparison, direct comparison, is this. If you compare your series to a convergent series, what do you want to see as far as the series you're comparing that you don't know versus the one that you do know? If the one you do know is convergent, then the one you are looking at has got to be less than that. And then you can conclude that that is going to be convergent also. If the one that you know about is divergent, like in this case, the 1 over n, then the series that you're looking at has to be bigger than the divergent series, okay? So smaller than a convergent series or bigger than a divergent series. That's the two ways that you can make a conclusion with direct comparison. If that doesn't happen, in other words, suppose you're comparing to a convergent series, and you find that the terms of your series are greater than a convergent series, direct comparison does nothing for you in this case. In other words, if this inequality sign is pointing in the wrong way, you can't use direct comparison. And then you have to use this other test, which we have called limit comparison. Limit comparison is a little bit harder to use, a little bit more work, but still much easier than the integral test. So let's see what the limit comparison test is and how it works. All right, so first of all, what I would say about these comparison tests, if you have the option, direct comparison is always better because it's just an easier test. All you have to do is just verify that, the thing you're looking at is greater than a divergent series or less than a convergent series. So what you should maybe do if you're asked to just check, does this series converge or not? The first thing you might want to do is just check to see if direct comparison will work, okay? And so regardless, you will always want to check to see what you're going to compare it to. So this step is for both of these comparison tests. Find out what happens for large values of n. So what is this approximately equal to? Well, the only thing on here is that -1, and so that's the term that's less than the cubic term, so it gets dropped off, and then we're looking at 1 over n squared. And then we would say, okay, what does this series do? 1 over n squared. What does it do? Well, that's a p series, right? And you can clearly see that the p is bigger than 1, so that's all we have to say about that one. 1 over n squared, we know that converges because it's a p series. Now, what I'm getting at here is you might want to just check for direct comparison. And if it doesn't work, no big deal, because it's such a simple test, you haven't really wasted much time, right? So what's my check here? I'm just going to check, how does n over n cubed minus 1 compare to 1 over, or actually, let's do it unsimplified form. Let's do it n over n to the third. Well, that's, like I said, it's very easy to make this comparison because the only difference is that, right, the minus 1. But again, if you subtract stuff from the denominator, what effect does that have overall for the fraction? Well, it makes it bigger, right? And so the problem with this for direct comparison is that is going in the wrong direction, right? Remember, to be able to use comparison versus a convergent series like this, you would want that sign to be pointing in the other direction. You would want to be less than a convergent series, but this is greater, right? So this is what's telling us that direct comparison is not going to work. So just point that out. This is going the wrong way for direct comparison. So that means, well, that's not going to work. Again, we haven't really wasted too much time here, but that's something you just might want to check. Okay, so what does that mean? Well, that means we have to use the other comparison test, limit comparison test. So this one is a little, like I said, it's a little bit clunkier to use, but it works. This one, in fact, works every time, even if direct comparison works also. This would still also work. Okay, so it says right there, suppose that an and bn are terms. If limit of the ratio of these two things is any finite number, then both the series have to do exactly the same thing. Okay, does that make sense? So let's identify like which one is which here. What are we wanting to do here? We're wanting to find a limit, right? Limit as n, this is why it's called the limit comparison test, because we're finding a limit of an over bn. That's what we're trying to do. Well, it doesn't even actually matter which one you decide to call an versus bn. So I'm just going to call the one we're trying to find out about, I'll call that one the an term, okay? So the an term is what we're trying to know about. So n over n to the third minus 1. And then I'll call the bn one the one that I do know about. That's the 1 over n squared, okay? So here's the an on top, n over n cubed minus 1. Here's the bn on the bottom. Now, what we're going to see, this is the only time I'm actually going to write it like this, as a ratio like that. Typically, immediately what you would do is just say, well, I don't really like to have those fractions over fractions. So rather than doing a division, I'm going to change it into a multiplication. Right? Just flip over that bottom one and multiply. And then take that limit. Okay, so that's n to the third over n to the third minus 1. And we all hopefully know that when you have the same powers in the top and the bottom like that, the limit is, as we go to infinity anyway, is the ratio of the leading coefficients. And so in this case, they're both 1, and so the limit is 1. Now, if you look at the conclusion that is necessary for this test to work, all we have to have is, this is the c value, okay? This is the c that you see in the theorem there. If that term is finite and positive, that's all it has to be, is just finite and positive. 1 is both finite and positive, right? So that's it. That's all we need. In fact, all we got to say is that it's greater than 0, and it's not infinity. Well, what is our conclusion then? Then it says either both series converge or both diverge. Well, what has to be happening here? Because we know what one of them does, right? As a series, we knew what that one does. It converges, right? So what does that mean about the other one? Well, they both have to do the same thing, so that means the other one also has to converge, okay? Everybody see what's going on there? So our conclusion is that the series we're after here, n over n cubed minus 1, converges by limit comparison test. All right, let's try another one then. Okay, so take a look at this one. Again, the first step here is decide what's happening for large n, for large values of n. What does this series act like? What do the terms of this series act like? What is this approximately equal to? Well, again, we just drop off all the lower power terms and then simplify it, and that leaves us with 1 over n. And then decide, as a series, what happens to 1 over n. And then why does it happen? This diverges. Why? It's a p series and p is equal to 1. Okay, now we know what we're going to compare it to. And again, you might want to just do this step. I mean, we know this is going to fail, but just for future reference, you might want to do this, especially if they don't tell you which test to use. If they say, well, use one of the comparison tests, but we're not going to tell you which one. You might just go ahead and just try direct comparison and just see what happens. And if direct comparison works, then you're done and that's it, right? And it's a super easy test. And remember, with direct comparison, leave it in its unsimplified form, and then just decide which way this inequality has to be pointing. Well, again, the only difference between these two is that this has a +3 and the other one doesn't, right? But adding stuff to the denominator, what effect does that have overall to the fraction? It makes it less than, right? But what we've just shown is that we are now less than a divergent series, but in order to use direct comparison, we would want that inequality to be pointing the other direction for direct comparison. We would want that to point the other way if we wanted to use direct comparison and make some kind of conclusion. Okay, so what does that mean? Doesn't work. Use LCT. Use limit comparison test. Again, if you're okay with limit comparison test, if you like it, or just, maybe don't even want to bother with direct comparison, even though it is easier, you can always use limit comparison. It will always work. If direct comparison also works, it will always work. All right, so then what is the limit we want to find? We want to find the limit of the series we're checking. And again, I'm not going to write the complex fraction here. I'm just going to immediately take that and then multiply it by the reciprocal of the other one. The reciprocal of the other one is just n over 1, right? Because I would be dividing by 1 over n, but dividing by that fraction flips it over. Gives us this limit here, n to the third over n to the third plus 3. And that limit is 1, just like the last one. And all we care about for a limit comparison is that that number is both finite and positive. 1 is both finite and positive. And so what is our conclusion? Our conclusion is that this series that we're looking at, what we're testing, has to do the same thing as the other series. And that other series diverges in this case. So this is an interesting test and something that you can, it's possible to get confused about this. I fully understand that. But if you see in that previous example, look what we did. We did all this stuff. We found the exact same thing, right? 1 was the limit. And yet in this particular one, we concluded that the series converged, right? Whereas in the other one we just did, we concluded that it diverged, even though we got exactly the same conclusion here, right? But why is that? Everybody see why we had to arrive at different conclusions even though we got the exact same result? Well, it's because of the series that we were comparing to, right? That's the reason for the different result. The first one we were just doing, we compared it to a convergent series. And so therefore the result was that both series have to do the same thing. So they both had to converge. Here, we were comparing it to a divergent series. And so when we reached this result here, we had to say, well, both the series had to do the same thing, and so this one must diverge also. Does that make sense? Any questions? Okay, yeah, so that's a good question. What happens, notice that what is required for us to use this test? The requirement for us to use this test is that this limit here, that limit, has got to be a finite positive number. What if it's not? What if it's 0, which is not positive, right? Or what if it's infinite? Well, in that case, you can't make any conclusion about this series, at least not with the series that you happen to compare it to. So chances are, if you do get 0, I would say the most common reason for getting 0 on this is that you chose the wrong series to compare it to, okay? That's why this step up here is important, deciding what series you're going to compare it to. If you screw that up and you choose the wrong series, it's possible that you might get 0 right here, or you might get infinity here. But that's still, all that's telling you is that that is inconclusive. It's not telling you anything about whether the series converges or not, okay? So if you get 0 or you get infinity, it just means the test fails and it is inconclusive. The series could go either way in that case. And again, probably what the reason for that is that you chose the wrong series to compare it to. It's also possible that this test is just not going to work at all and you have to use a different test, okay? All right, so this part C is slightly different because the series we're actually going to compare it to is not a P series, so that makes this one a little bit different here. So let's check part C here. But really, there's only two types of series where you can actually just tell upon inspection whether or not it converges. We've seen one of them, actually we've seen both of them already, but one of them was the P series, right? All you got to do is look at it and see what P is. But we've actually already seen one where you can tell whether or not it converges simply by looking at it, right? If you remember, geometric series have that same property, right? Like, what is a geometric series? A r to the n, and we know that as long as that r is less than 1, then it converges, right? And if the r is bigger than 1, it diverges. So this is another one that just you can tell upon inspection whether or not it converges. That's a geometric series. So it turns out that's in fact exactly what we're going to compare this one to, the 6 to the n over 7 to the n minus n. Anyway, regardless, we still start exactly the same way. So if we say for large n, 6 to the n over 7 to the n minus n, and this works the same way for exponential functions. The exponential function dominates any other type of function, for example, a polynomial function like that n. And so we neglect all lower powers or lower, slower growing terms and realize that this is that. And then you can say, okay, well, what does that do as a series? 6/7 to the n. But now we can recognize that that is in fact a geometric series, right? And that means that this thing has to converge. And again, I would like you to tell me the reasoning why, because it's geometric with r less than 1. So that's the reason we know why 6/7 to the n is going to converge. And so now we've got something to compare it to. And again, you might want to just check for direct comparison here. But I mean, I think you can probably see that it's not going to work because unfortunately we have that minus n there. The subtracting stuff from the denominator, what effect does that have? It makes the fraction larger overall. And in order to be a candidate for direct comparison, we would want it to be smaller. Okay, so we can see pretty obviously direct comparison is not going to work here. So let's just use limit comparison. We'll take the limit of the series that we're interested in, right? The 6 to the n over 7 to the n minus n. Multiply it by the reciprocal of the other one, so that's going to be 7 to the n over 6 to the n. And then see what happens. These 6 to the n terms we can cancel, and we're left with this. Okay, now that is actually a indeterminate form. Remember that. This is infinity over infinity, right? And so indeterminate form should tell us L'Hopital's rule, right? And L'Hopital's rule then tells us that we need to take the derivative of that top function. And that's going to be 7 to the n times the natural log of 7, exponential function, right? 7 to the n also in the denominator, ln 7 minus 1. But that still gives us infinity over infinity. So we have to use L'Hopital's rule one more time. And so we'll get, again, by L'Hopital's rule. So if I do that again, I'm going to get 7 to the n times ln 7. Now it's going to be squared. Same on the bottom, 7 to the n ln 7 squared. But now the minus 1 is gone, and now I just have everything is exactly the same in both the numerator and the denominator, right? And so that limit is just 1. And again, 1, all we care about that for limit comparison is that it is finite and positive. It certainly is. 1 is both finite and positive. So that means both series have to do the same thing. And since the one we compared to converges, so must the other one that we're looking at. And the reason, again, by limit comparison test. All right, so I want to give you a chance to try a couple of these. Okay, let's take a look at these real quick. So I'm just going to point out that there's another way that you can do that direct comparison. Is what Michael's doing. I think what you did here, you didn't have that filled in, right, Michael? You didn't know what that was right away?
Correct. I just had the empty box there.
Right, yeah. So he starts out by putting a box there, like unknown, what that's going to actually do. And then cross multiply, right? So if you take this times this, and then this times this, you get the next step right there. And then you just keep doing this and step by step simplifying it until you get to this point right here where there's no question that that's true, right? N to the 1/2 is definitely going to be bigger than 0. And once you reach that point, then you can just go back and say, okay, well, that thing greater than, right? And so that means it can't have changed. And so you just fill in those all the way back to the top, okay? So that's another way to tell if you want to, if you don't have it in its unsimplified version. If you're trying to tell which way that inequality sign is going to point, you can just put a box there and then cross multiply, simplify as much as possible. And then once you reach that step at the end where it's obvious which way it's supposed to point, just go back and fill in all those boxes with that same direction of inequality. Does that make sense? Going on there? So that's another option if you want to do that for determining whether or which way that inequality is supposed to point. The next one, yeah, similar situation there. I think it turns out that all of these converge by direct comparison. Is that right, Michael?
The first one and the second one did. The second one I did it two ways: direct comparison and limit comparison. And then the
Right.
third one I did limit comparison. And
Okay, I
also,
think that third one also works by direct because the plus three in the denominator makes it smaller, right? Being smaller than a convergent series means convergent, right?
mhm.
So part C could have been done by direct comparison also. And I think even part D, if you look at all the terms that you get there, you did that by limit also, but that one actually I think can also be done by direct comparison. But anyway, either way is fine.